So our next speaker is Dr. Yuandong Tian. Dr. Tian is a research scientist director at Meta GenAI. He's also leading Llama reasoning group, team. And, and I read quite a lot of papers from Dr. Tian. I think early, I think he had a project on this Open Go project, which is sort of looking at AlphaZero. I think Dr. and also working on multi-agent learning. I think the recent paper about large language model reasoning, I think it was about pause tokens. So the idea of, say, maybe we can do this reasoning not necessarily in the language domain, but maybe in the latent domain. I think that's definitely a very interesting direction to look at it. So please welcome Dr. Tian to tell us a bit about this. How can we unify, the neural and the symbolic decision making? Please.
Can you hear me?
Yes.
Okay, cool. Yeah, thanks for introduction, Dr. Wang. My name is Yuandong Tian. I'm a research scientist director in Meta GenAI right now. I have been in FAIR for 10 years, and recently we joined the Meta GenAI team. I'm one of the research lead, but not all of them. So I saw there are actually some other research lead as well on the reasoning side for Llama. So I just joined for 3 weeks. So of course, there's lots of things I don't know to some extent. So I don't treat me as a full-fledged lead for that efforts. So right now, so we are busy with all the release right now. Hopefully things are fine. Today I'm going to give a talk which is mostly academic. So towards a unified framework of neural and symbolic decision making. Basically, like the direction here is that we want to work on language models, and we all know language model is very important, and there's a lot of applications. So in our group, we mostly focus on reasoning and planning, right? And when we work on reasoning planning, we often ask ourselves the questions like, what kind of problems that a large model cannot do very well? The answer is, of course, like the planning problems, right? So for the travel planning problems that I often use as one example, the language model actually cannot do very well. So the travel planning is very simple. You ask the user to provide a request to the language models, and so that the language model can give you the travel itinerary that satisfies all these requests. Right. So for this kind of planning problem, usually people will think about this kind of agentic behaviors, right? So the LLM will first collect information and then give it a plan according to all the constraint, budget constraint, as well as the as a kind of common sense constraint, and put them together into a plan, right? So that's actually the idea, right? So of course, like if you ask the model to do that, it's actually not doing very well. This is actually one of the papers that we published last year, early last year. It's kind of an old paper according to according to large model kind of speeding pace, right? So I mean, 1 year is like 1 century in the community of large models. So what happened is that even the soda models struggle for hard planning problems, right? So at that time, the best model is the GPT-4 Turbo, and you actually see is that if you ask the model to do planning for the travel, you actually only give you like 0.6% accuracy for the final pass rate, which means that the final trajectory is completely correct and satisfy all the constraints of the humans and also of the common sense constraint. So it's actually very, very low. So if you even you allow the model to access to the ground truth tools, and you have all the background information, and you don't need the models to actually extract them. You only ask the model to plan, then the model only give you 4.4% of final pass rate, which is actually also very low. Right. So of course, like people will say about R1, talk about O1s, right? So currently we only have O1 preview numbers because this is an out of date slide to some extent. But with the O1 preview, you only see the performance basically go up a little bit, but not too much, right? So you only see the final pass rate to be 15%, which is not ideal. Of course, it's much better than the 0.6%, but it's still not super high compared to if you think about like if the problem can be solved by symbolic solvers. Same trend happens to other kind of large models as well, right? So if you check the previous Gemini 1.5 reports, and what you see is that they are trying to test their approach on the planning, and you see when the scale of the problem becomes higher, larger, and you see the performance all drop to zero. Right? So this also happened to this plan bench, which is from the ASU, and they also report that the O1 preview approach is not doing well when the plan become more and more complicated. Right. So recently we also have another paper called GSM Infinite, and that paper actually also shows that the same thing also happens to all the state-of-the-art models, including DeepSeek models. Right. So you'll see this this kind of decay when the problem becomes complicated. So it's not like the model is solving this kind of planning problem with test time compute, but you still see the problem there. Okay, then the question is really like, what is the solutions? Radar solutions, right? So there are several different ways of doing that. First of all, of course, you can put more and more data into the scaling laws, and hopefully the scaling law will help. And the second is that we want to leverage like test time scaling, right? So we can use large model plus tools, large model plus chain of thoughts, and hopefully with this test time scaling, test time usage of different vehicles, and we actually end up with a solution that can do better than large model alone. And finally, I will briefly introduce our recent theoretical studies that I try to unify the symbolic structure from the with the neural network representation. So you can actually find there's actually symbolic structures emerged from the training of neural networks using gradient descent. And by doing that, you actually see unification of the symbolic representation and neural representation in the same framework. But this is very rudimentary, and hopefully this might be in the future become mainstream later, but we don't know. So I'm going to cover all these aspects. So of course, like in option one, you need a lot of compute, a lot of data, and it's very expensive, right? So we are not sure whether it works on reasoning and planning. And option two is the test time scaling. So here I'm going to talk a little bit about these two parts. First is tool use, and second is using chain of thoughts. So for tool use, what we do is that we actually can call external tools in order to address the problem of reasoning, right? So we just take this travel planner problem as one example, right? Instead of having the user to having the model directly answer the question provided by user, what we can do, we can detect the tool. The tool basically says that you start from a user request, and you first use large models to translate that into a symbolic form. So this symbolic form basically characterizes accurately what the user really look like. And together with the flight hotel information from like external world, you can basically put them together into a big like optimization problem, and you solve that with the mixed interlinear programming, which is a combinatorial solver. And that solver will give you the symbolic representation of the optimal itinerary, and you can basically translate that back using the existing large models, and then you get the answer provided by the agent. Right. So by doing that, you're able to give you a guaranteed solution, and at the same time, it's not that slow. It's actually pretty fast if you go through the entire pipeline. So we actually built a demo on top of that. We actually show that with 2 or 3 seconds, you're able to get a solution that's guaranteed to be correct, given the user's request. I mean, also given the condition that the translation with the large models is actually pretty accurate. So you can see there's a 2 or 3 seconds delay, but the overall demo can still be run. And we also test with our human annotators, and look like they are very positive about the results. Of course, like if you think about the trial planning, we also want to let the agent to clarify questions, right? So we want the agent to really think about like what are the details that is missing from the user request, and the user whether the agent can actually ask more and more questions to clarify that, to make sure that they understand. So this actually motivated us to work on a follow-up paper on like how to build this multi-round dialogue so that the agent can interact with humans more effectively. So we basically build that by asking the agent to follow the agent constitution, right? So basically the agent needs to be evaluated according to several criteria. And some criteria are actually very objective. Some criteria is very subjective, for example, the credibilities. So objective means that the agent needs to finally get an answer, that answer is accurate. And also the agent need to be very proactive in asking the right answer, right questions for that particular persona of that person, right? So agent also need to be efficient in asking all the questions before it get into the actual solutions. Yeah. So we basically do this iterative DPO and reject sampling in a iterative manner, and we've shown that the AB models and train this manner can be much better compared to the original 70B model that does not going through this training in terms of multiple access. Okay, so this is the first part that we actually can leverage a tool to solve the complicated planning problems. And the second part is that I'm going to talk a little bit about large model plus chain of thoughts and how you construct chain of thoughts to solve these hard planning problems. So in order to start with that, let's start with this first paper that's called a search former. So in this paper, we construct chain of thoughts using the trace of existing combinatorial solvers. Right, so when we think about this maze navigation problems, right, we have starting points and then we have ending points, and we ask the model to find what is the shortest path between the starting and ending point. We can either ask human to annotate, or we can ask the symbolic solvers to formulate the problem and to make the problem to solve the problem while doing a kind of symbolic search. So what the A-star problem, what the A-star will do is that it will open a priority table. That table will basically like find what is the right next cells, next states of the search to be explored. And then following the way for exploration, then we finally find a path to the destinations. Right, A-star search will have guarantees, and then it will guarantee to give you the optimal trajectories. So following the A-star trajectory, the search process, we can actually construct the chain of thoughts as follows, right? So we start with the prompt, which is the representation of the problem specification. And then we can construct the trace by basically like a dump all the A-star search procedure. So every time the A-star search create a new node and in the search space, we actually put a create in the trace, right? Every time A-star actually close a node, then we put a close there. So we basically put this long trace there, and then finally, once A-star start to find a goal, we basically put a plan, which is outputting the actual final trajectory, which is the optimal trajectory. So this basically give you this basic framework of the search augmented model, right? So we have a prompt as the input, and we also have asked the model to generate the trace as well as the plan. This is in contrast with the solution-only models, in which we start with a prompt and then we ask the model directly output the plan. Right, so and of course the number of tokens will be very different, right? So this paper was basically published early previous years, 2024. In that year, I mean, people haven't realized too much the power of using very long chain of thoughts to solve complicated planning problems. But now I think everyone actually realize, and people are embracing very long traces for solving the problems. So we find that using this trace augmented search augmented models, what will happen is that, I mean, the scaling law is very different, right? So we actually see that if you only use solution-only models, then you need 1 million samples in order to achieve almost 100% accuracy. But if you use search augmented models, then you actually use 10x fewer data, and at the same time, you use 10x fewer parameters in order to achieve similar performance. So the search augmented model is much more sample efficient and also much more parameter efficient. So this happen to be the same for other kind of like color planning tasks like Sokobang, right? In which like the agent need to push the boxes to the destinations, but it requires very careful planning because if the box was being cornered, there's no way back, and you have to basically backtrace. Yeah. Okay, so once we have the search augmented models, which is basically done by imitation learnings, one thing we can do better is by doing fine tuning on top of this search augmented models. So what happened is that we can fine tune the augmented models so that it will give you shorter traces, but still leads to optimum plan. So this is a very typical reinforcement task because the goal is clear, but how we achieve the goal, we don't know, right? So we ask the reinforcement agent to basically like search around and find the solutions. Yeah, that's the search formula. And by doing search formula, we actually see that it actually end up with like a better model that has a shorter search trace compared to the original A-star search because of this iterative address sampling, which is a poor man's version of reinforcement learning. So we actually see this happens. And in terms of the numbers, I mean, we see that the ratio between the reduced trace and the original A-star trace is getting higher and higher, right? So which means that this is indeed the case numerically. And not only that, but we also find that the not only the trace becomes shorter, but also the performance after fine tuning is also getting higher, right? So the ratio of the solution being optimal is getting higher and higher after each of the iterations. So this basically, and after 3 iterations, you already see that the model with 45 parameters, million parameters, is actually comparable with the model trained with like a 700 parameters and trained with like a much larger data set. So this is actually very interesting, and I believe that this is one of the very few papers at the beginning to show there's actually a scaling law on the test time and also on the training on the like reasoning data that can substantially improve the performance of the reasoning tasks.
How about the generalization? I would be very interesting to say, you know, the language model could generalize that to some other domain which haven't been trained on.
Yeah. So I think we have tried several generalizations, right? So for this paper, there's no much generalization going on because we only train on the Sokoban or on the maze. But in the follow-up papers, we actually see that things can generalize a little bit. Yeah, for example, we can generalize to like different sides of the mazes. That's actually one way of thinking about that. And we put like a multiple and we can also like try these ideas to, for example, math problems, and it can also generalize and give you better solutions on math problems.
Okay, good.
Yeah,
So for the trace, if you sort of maybe generalize that the trace, transform that trace into sort of have certain semantic meaning, like I don't know, with some kind of language,
yeah,
uh, would that help in terms of generalize to maybe math problem, or because all this search principle, they are essentially the same, right?
yeah.
Maybe you can learn.
I'm actually not sure because what we actually do is like on the other side, we want to start from like text-based tokens, and then we can basically make it latent tokens or latent continuous representation, and then this might be more efficient. Yeah,
Yeah, it could be. You could down search in the latent space.
yeah,
Yeah.
yeah.
Sorry, have you guys, I mean, we're working on embodied AI a lot, right? So have you guys tried to develop a VLM version of this? Like something that takes the image of the environment, because it might be nice for planning in embodied environments, actually.
Yeah, I think we haven't done that yet, but I think that should be quite straightforward, right? So yeah, so you just follow the same path, but you basically render every state as an image, right? So in that case, like things might be a little bit easier. So for
Yeah,
example,
and give COT as like images instead of
yeah.
this.
So
Yeah,
yeah,
I see. Okay.
so here you have traces, right? So this is actually not that intuitive, right? So if you can render images, you basically here's like the current status of the search space, and then you basically stack these images together as the visual chain of thoughts. This might also work well.
Yeah, but then we have a long context issue, right? Because
Yeah. So
uh,
of course, like you can always do some kind of compression on
yeah,
the
yeah. Okay,
yeah. Yeah, I'm going to
cool.
talk a
Thank you.
little bit about like how can we use VQVAs to do that.
Okay. Thank you.
Yeah. So okay, so that's the search former paper, and once we have search former paper, then we have follow-ups, right? So we have one paper called dual former. In that paper, we basically try to reduce the size, the length of the trace being used for training, right? So you can randomly like dropping tokens for the search traces. And these dropping tokens, you can have like a multiple way of dropping tokens. You can drop like, for example, all the clauses, all the courses with all the costs, right? So you can also even drop all the entire trace. This means that we are essentially trained on a mixture of the solution only and the search augmented data together. And this training actually turned out to be very interesting and actually give you some model that is very is powerful, right? So we actually end up with this deformer model that I can automatically switch between the fast mode, which means that you directly give the answer, and the slow mode, which is basically give you chain of thoughts and then the answer. right? So you can have a model that can do both at the same time, and at the same time it actually works better for dedicated models on either modes. So this is actually very interesting. The way we switched between the two is very simple, right? So you just ask the first generated token of the dual formal to be either a beginning of search token or a plan token that will end up with a direct optimal answers. Right, so you only basically fix the first tokens, and the model will behave very differently, and it would behave either like a faster mode or the slow mode performance. Right, so it's actually interesting to see that it's actually better than fast mode alone, and better than small mode alone. So that's interesting findings after we train these models. And we actually noticed that DeepSeek also show like similar behaviors. There are some tricks in the DeepSeek thinking mode, right? So you can actually make sure that if you have two space after the thinking tokens, then the model will tend to be a little bit longer in terms of the thinking sequences. If you have not two space but two returns, if you only have one returns after the thinking tokens, then the model will tend to be a little bit longer in terms of thinking process. Or vice versa. I didn't remember which one is which, but you can definitely check the interesting structure there. I think this is probably because the data they use to train a model will have this kind of specific structures. Then this will actually be learned by the models in order to control the model behavior as a side effects. And we're actually happy to see that the similar behavior happens in these state-of-art large models. Yeah, we also apply the dual former into like math problems, right? So the baseline will have like very long chain of thoughts, but once you randomly drop in like sentences and then use this to do fine tuning, very surprised to see that the length of the sequence will have a very basically the thinking tokens are very short and become much shorter. And at the same time, it's still reasonable, right? So and it will give you the answer that's correct. It's kind of interesting behaviors. We actually do this mass tuning on the base models. These are they are base models. They are not mass specific models, so the performance is not great. But you still see that the performance goes up a little bit, right? So after you do this dual formal training, right? So performance actually go like a little bit. Yeah. Okay, so this basically conclude like our work on the token space. And then we're going to talk a little bit about our recent work that try to get into like this latent space. So one of the paper that actually went viral last year is the coconut paper, in which we're trying to replace the discrete tokens with the continuous tokens, so that we actually arrive at like a shorter chain of thoughts, and at the same time, the continuous version of chain of thoughts may have interesting properties that we don't expect, and we see it might be interesting to explore further. Right. So the idea here is very simple, right? So the traditional chain of thoughts has discrete tokens as intermediate stages of thinking, but why here we want to try to basically construct like a continuous tokens to do this thinking process. Very simple. So the training procedure is actually straightforward, right? So we start from this stage 0, which every step is every step represents a sentence of discrete tokens to do reasoning towards the answers. So every time we do the training, we do the curriculum training, we start from stage 0, and then we gradually replace every step into with the actual thought vectors. So we do that. And we train on stage 1 for a while, and until it stops, until it converges, and then we train on stage 2 and until we train on stage n. Right. So and in that case, like all the discrete steps, discrete sentences are replaced by the continuous thought vector. So that's very simple, kind of straightforward training process. Yeah. So what happens to the results? So here's like several examples that I can share with you that if you train the model this way, then the model will behave very differently than the discrete chain of thoughts. So we mainly test this approach on synthetic data. Synthetic, which means that you actually construct a graph between the starting nodes and ending nodes, right? So basically, the graph has lots of like directed edges specified by the actual sentences, right? So here you see that so for every lumpus is a yumpus. So this basically means that there's an edge between the node lumpus to the node yumpus. So this actually basically this sentence actually give you the graph that you want to study, and the answer is basically like one of the node that can be connected from the starting node. Right, so the question is Alex a grumpus or grumpus, which means that is that an edge between Alex and the bumpus, and is that edge between Alex and the grumpus? Right, so that's a very simple kind of graph reasoning task in this case. So of course, like there's a ground truth solutions by constructions, but there's also a lot of solutions that is actually very misleading and may lead to wrong answers. Right, so because the graph is complicated, so if you just run train of thought, then what happens is that the chain of thoughts may make the mistake at the beginning, right? So once it made mistakes at the beginning by like checking, okay, if you go left, right? So and you eventually will find you actually end with a node as a dead end. There's no way you can go all the way to the destination. So in the chain of thought case, because it goes to the local minima, so it has to hallucinate an edge all the way to another node of the graph so that it will continue to reach a destination, which is wrong. But in our case, if you train our models on this data set and test on different examples, what you see here is that while if the channel size is short, when it becomes longer, and suddenly it will give you the correct path from by the 2 hops because the optimal trajectory is 2 paths. So it's actually very interesting. So people, we actually have some ideas about why it works, right? So and here's like some summary about like what's happening inside this chain of thoughts, continuous chain of thoughts process, right? So for example, like if you just do one continuous chain of thoughts, then you can also once you have this continuous chain of thoughts, then you can ask the model to decode on the next step about the next node that it may be able to decode, right? So then what you see is that the model seems to already know which node is already a dead end, because the corresponding probability in the after softmax already encoded implicit value functions, whether it is actually dead end or not, right? So for example, here the stereopus is actually dead end, so the corresponding softmax function actually give you a very low number in terms of probability, right? So this is dead end, and the other 3 they have pretty high probabilities. So basically, the model after training actually learn these structures. So if you do one step further, then you have basically 2 continuous source vectors here. And these 2 continuous source vectors after that, and then you ask the model to decode that particular tokens. And you will see that different tokens will have different probabilities. And this probability actually really correspond to the connectivity of whether these nodes will connect to the final outcome of the possible destinations, right? So these 2 are dead ends because there's no edge as it's going out. So their corresponding softmax values is actually very, very small, right? So, but there's some node that actually has very high probability, so especially this one. Yeah, so because it's very close to the actual solutions. So basically, it looked like in the continuous channel source settings, interestingly, it encodes all possible passes. The intermediate, like a latent and continuous representation, actually implicitly encode all possible passes, so that when you do the search, it's actually going through all different passes until it hit the right answer. And then you can basically directly, given the right answer, you find like what's the best path to go. So this seems to be like a very efficient way of doing search, right? So if you think about like how we do this in the discrete space, then what happened is that the discrete space have to do Bing search to basically encode all the possible combinations, and then you do like a branching, and you do probing, you do pruning until you find destination. But in the continuous space, look like multiple possibilities can be superpositioned together until you find the right answer, then it will decode correctly. So that's something that's kind of
last question. So here you have this probability of rompers, and have this factorize this into like a RO, RP. So how you derive this?
Yeah, so sorry, this is because of the tokenizer we use. So we are basically trained on the same tokenizer as Llama. So the tokenizer will basically break it into 3 pieces. Yeah.
Okay, and then you calculate that from this the second to last layer to get that probability.
Yeah, exactly. So basically, like when you already consume these two continuous channel of thoughts and also consume this EOT and every token, right? And then you want to basically generate the next token. Then what you do is you can basically plug in possible outcomes and then check the probability, right?
Okay.
Yeah.
And then you basically say if you have two thoughts, the probability of that would be higher. Is that
Basically, if you have two thoughts, means that you actually do a two-hop search, right? So you do two-hop search, then this probability actually contain all the possible outcomes, and this outcome, the probability, look like they are correlated. They are very correlated with whether the future node will be connected to the end, the destination that you want to go.
But how do you know these two thoughts is actually corresponding to two hops?
So I think because each thoughts, when we do the training, we actually have every thought represent a hop. So basically, this is by design. You train this using this kind of structure, then you know each thought corresponds to one hop in this
I
synthetic.
see, I see. Okay. So this is more like kind of controlled experiment, actually demonstrate what's the meaning of that.
Exactly. Yeah.
Okay, got you.
Yeah.
This is very interesting. Do you know why this happens? Like there seems to be a notion of a value function or something somewhere, because like where is this encoded?
I think that's the interesting part of this paper because we don't know yet. It looks like it's actually encoded value function, but the value function is
Right.
automatically. Yeah.
It's interesting. Okay. Very interesting.
Yeah, it's kind of learned automatically from the training. We don't know, we have no idea what is the value function. We just train the model like this way, and then it give you these solutions.
I think might be worth to plug in this MPC into it, right? Because when you have an MPC, because you already got this correct trajectories.
Yeah.
And then obviously you don't let them know, but then let this MPC running underneath this thoughts. You know, and then maybe on roll this MPC, and you can actually understand this dynamics and how this gonna you know can generate the correct trajectory as you given. I think it's yeah, it's very interesting. Yes.
Yeah. So I think one interpretation is that it's possible that this latent space may encode some superpositional structure of the graph, right? So basically, like if you think about like quantum systems, then any kind of discretization is kind of measurement from the quantum superposition, right? So by basically taking the product and then the sample from it, right? It's exactly the same as doing like quantum measurement, right? So, but if you don't do measurement, you just use the superpositional state to do compute, then the superpositional state may encode all the possible passes at the same time by superposition all the possible passes together. And then finally, once you reach the destination, then you just decode, and maybe it's much more efficient than just do like a discrete token chain of thoughts.
Yeah, quite nice analogy. Yeah.
Yeah, so that's one possibility, but we don't know. It's
You might want to using a quantum formulation to really understand it. But
yeah, so that's one possible explanation. From when I saw these experiments, I feel like this may be one of the reasons, but we don't know. Yeah, we
I
will.
see. That's why you say I don't do the super what the super so basically you don't do the measurement. Therefore, you don't generate tokens. Rather
Yeah,
you keep the thought running
yeah,
until
yeah,
you measure it.
yeah.
Right. Okay. Interesting.
Yeah, that's one possible explanation, but we don't know. There could be other explanations. Yeah. Okay,
I
so
think maybe
yeah.
Sorry, just one last thing. I think maybe if we look at it from a value function perspective, we might get some information. And maybe these softmax are encoding some value information, actually.
Yeah. I think so. It's definitely possible. Yeah.
Yeah.
Okay, so we actually checked the performance in the synthetic dataset, which is called the PROS-QA. So it's basically the dataset that I mentioned before. You construct a lot of graph edges, and then you ask the model whether the two nodes are connected or not. So, and we show that with like a longer and longer thought thinking process, and our approach getting better and better. compared to channel source, because channel source will have a lot of incorrect passes, and also some of them they will have hallucinations, right? So that's actually showing the strength of this approach. Of course, this approach is more like experimental research purpose. So the performance on the GSM-AK is not great. If you compare to the channel source approach, I mean, you have fewer number of tokens, of course, because we are using continuous channel source, but the accuracy is getting a little bit lower than the COT. But it's actually better than all the non-COT approaches. Right? So of course, that's on the synthetic data sets, we actually see the performance is great compared to all the results, especially the cross QA, right? So, but for channel source cross QA, performance is worse because there's a lot of like hallucination happening and a lot of dead end that the channel source will get into. It get confused, but our approach is getting very well. It's doing things very well. Okay. So of course there's some weakness of this paper. So first of all, the latent tokens are not interpretable. People already asked these questions, right? So if you start with latent tokens, and what the hell is going on inside the network, and maybe it's not safe for humans. And the second is on testing on GSM-AK for real data sets. So we have actually another paper that recently released, which is called the token assorted. And that paper is basically doing a mixture of continuous and discrete tokens in order to train the model better, right? So we all know that the regular COT, they are basically doing text-based tokens, and then you use that to do training and fine-tuning. But for our assorted COT, what we do here is that we actually convert some part of the channel source chunk into the latent discrete tokens. So this will actually make the COT shorter, but at the same time, it also will increase the performance surprisingly. So that's actually the idea, right? So how to compress the COT? We can actually use VQEAE to do that, right? So given these COT tokens, we basically first chop it into chunks, and then for each chunk, we basically use an encoder to encode that into latent vectors, latent tokens, and then you replace the COT with the latent tokens. Then you will have you basically have like shorter traces to train on. And here's the performance, right? So we actually show that with this shorter sequence and also the sequence that contain the latent tokens, our approach actually gives you better performance than other approaches, including COT. It's better than COT in many kind of math problems. The gain is it's around like 4 to 5%. So in absolute numbers. So know that all these three models, they are basically base models, so it's not a fine-tune on the math. So the performance is a bit low. If we fine-tune the math, I expect like an even higher performance. At the same time, you see the COT is getting shorter, right? So this is basically the length of COTs for each of the models, and you see that we actually can get an average of like a 17% dropping in terms of the COT length. At the same time, performance is getting better. So it's actually very interesting. So how we train it? The training is actually also very straightforward with some simple tricks. So here we start with COT, and then we replace some of the chunk of COT into the latent vectors, latent tokens, right? We are doing this AI called the autoregressive replacement. So we first randomly draw a location of the COT, and given the location, every chunks of the COT will be replaced by latent tokens, and everything else after the location is keep fixed as a text-based COT. So then we have the prompt, latent, text-based COT, and solutions. Put all these four together, and then we train the models accordingly. It's very simple. So and it's also fixed into it's fit very well into the existing autoregressive training pipelines. Right? So this actually makes the experiment pretty straightforward. And we see that our approach is actually pretty working quite well compared to like a naive replacement. So you can either replace all the COT chunks with all the latent tokens, but it looks like the pre-trained model is not adapt to it very quickly, so the performance actually drops substantially. Right, so you can also do like a curriculum replace, right? You can basically replace one at a time, but this is actually pretty slow. I mean, actually our coconut training is pretty slow, but our mixture strategy is actually very efficient, and it also leads you the best performance, right? So you can clearly see that this token assorted paper is a combination of this coconut and also a combination of the dual formers. Right? So put them together, and we actually end up with a better approach that can do both. Okay, so this concludes the second option. I'm not sure how many time do I have. I have like 1 hour, right? Okay. Yeah, so I think that should be the case. And let's do the option 3. I want to be a little bit faster here because there's a lot of math. So I want to only give you like a very rough idea about what is going on here. So traditionally, we also think about like a symbolic structure and also neural network structures as two dichotomy, right? Two different concepts that cannot be compatible with each other. So sometimes we think, oh yeah, we are using symbolic structure, we use symbolic approach within neural approaches, and they can be combined at high level, right? So, but here I want to show you some recent progress that it's possible that you actually can see symbolic structures emerged from the deep learning trainings. You train deep models and you kind of examine its solution, examine the solution, and you realize that the solution is actually having nice symbolic structures. So that's actually something that you can, it's kind of surprise for people to think about that. Maybe in the future, these two representation can actually be unified. That's why we have this title called Towards Unification of Symbolic and Neural Decision Making. Right. So this kind of like a thinking is actually related to kind of like a long-lasting debate about how a larger model represent knowledge, right? So there's basically two different school of thoughts, right? So one is basically saying, oh, a language model can do anything if you scale up the parameters. So basically, LLM actually show emergent behaviors when the parameter become higher and higher and more, then you actually see everything suddenly works very well. Right, so that's actually one of the very optimistic thinking. But on the other hand, people also criticize the language model's performance, saying that our language model may be just doing retrievals. So maybe we just like remember all we have seen in the pre-training data sets. And what we do is basically finding this data in a very mechanic way, right? So that's one way we can do. I mean, there's a lot of evidences, right? So recently there's a paper from Apple showing that if you do some, you add some like unrelated sentences of all the prompt of the reasoning task, and all of a sudden the performance of all the reasoning model, they drop substantially, right? So that's a very surprising findings, and also may support the idea that LLM is still not robust and doing like literally memorization, right? So of course, we really want to basically like break this to basically like get into the black box of large models to understand that better, right? So that will be very nice to understand. So for this particular project, I'm basically using a very simple reasoning task called modular addition. So in this modular addition task, what happens is that you have two numbers A and B, and you want to ask the model to predict the result of additions, right? So predict C. So both all A and B and C, they are basically from between 0 and D minus 1. So this kind of more modular addition. So if you exceed that limit, then you will walk back from the beginning. So if you intuitively, what you see here is that if you train the neural networks on this very simple task, right? So given A and B, you ask the network to predict C, it will basically memorize this table, right? This is called addition table, as we have done in our childhood, right? So you have implicit table to memorize them, and then you do retrieval, you get a correct answer. But actually, what happens is that people already perceive that if you ask the model to train these problems, the learned representation is not one hot representation. It's called Fourier-based representations, right? So you will actually see a lot of sine or cosine in terms of representation in the representation space, and basically the model is using the sine cosine to do addition to do addition for these particular tasks. So this has been supported by many papers, right? So here's like two papers I just put here. One paper is from 2024, and the 2025 I saw a very interesting paper which also give you the same kind of knowledge. So this thing sounded very surprising because people usually think this is counterintuitive, right? So it seems like it can use a different representation to do that. So in my particular like work, so I'm trying to basically make this a study as minimal as possible, right? So here Here we only use like two networks, right? Two layer networks. One is the networks have two layers. So the bottom layer and the top layer. The bottom layer has weights, and they take this one Hall representation A and B, and then the top layer is basically like also one layer of weights and the output some representation of C. And the loss is very simple. It's kind of layer two loss. Right? The loss basically say you want to minimize the output of the two layer network and the distance between output and the one Hall representation, the ground truth solution C, in a L2 manner. Right? So very simple approach. And you actually, what you actually see is that even with this very simple problem setup, once you train the models, you actually see very nice solution structures from the gradient descent trainings. Right, so here's the graph where I visualize the solutions. So the x-axis is basically like the number of hidden node index. And so basically here you have 20 hidden nodes in the neural networks. And the y-axis is the frequency of each of the weights transformed into the Fourier basis. Right. So for each weights, you may see the weights will have like some structures and can be visualized more easily in the Fourier basis. Then what you see is that indeed it learned Fourier basis, but also it actually show this very nice global structures of the solutions. Right. So for example, here in every frequency, you actually see all the 6 solutions, which means that every frequency is covered by 6 different neurons. So here, every frequency is covered by 4 different neurons, right? So for 6 different neurons, so this is called L6 solutions. You also can see that all the 4 solutions, so which means that some frequency is actually covered by like 4 different neurons with some kind of like a flat kind of biases there. So you can see this kind of 2 different solutions. One is called order 6 and the other called order 4 solutions there. Right. So, and if you scale this the entire problem up, right? So from d equals to 7 to d equals to 33, you can actually see like also very simple similar behaviors. You get you basically in terms of histograms, you see these 2 kind of order of solutions. It really happens. So if you scale that to even higher scale, right? So you have like a d equals like 127, which is like a larger. It should be supposed to be a large table for additions, right? So what you see is you also see all the 6 and all the 4 solutions there, right? So even if like here like the hidden neurons is like 512, which is a lot, but for each frequency you only have 4 or 6 neurons representing it for the entire solutions. So that's actually very interesting, and we have very kind of complicated but very nice mathematical formulations to show the solution actually can be composed from like a small and partial solutions, and this will basically form the entire algebraic structure of the solution space. Right. So in order to do that, first of all, you want to basically like decompose the L2 loss into the following form, which seems to be complicated, but has very nice structures that are compatible to the weight structure. And you can also show that the weight structure is forming semi-ring group, semi-ring structure, algebraic structures. And put them together, what happened is that you can actually show that like if you have a partial solution that satisfy like one of the terms of the loss functions, if you have another partial solution satisfies another part of the solution structures, then if you multiply these 2 together, the multiplication is using the ring multiplication, then this solution will basically satisfy both of the constraints in the loss functions. Right, so if you do this iteratively, then you start with these partial solutions that only satisfy that only will give you zeros in some term of the loss functions. If you combine them together, then naturally you will end up with a solution that give you the global optimizer for the entire MSC loss functions. So this basically giving you a way to construct the solution explicitly, rather than rely on gradient descent to give you the solution. Right, so following this approach, you can actually construct different solutions. This includes all the 6 solutions that you perceive, all the 4 solutions that you also see, and also all the D solutions that correspond to the perfect memorization. Right, so perfect memorization basically means that you are memorizing the entire addition table in the neural networks, and then you do retrievals. Right, so but this all these solutions actually very high order. So when doing the training, the gradient descent would prefer to use kind of lower order solutions. So what makes this kind of construction interesting is that if you actually check the gradient descent solution, they actually follows what the theoretical construction look like. Right, so first of all, if you take all the gradient descent solutions from the experiments, and then first of all you check whether they are order 6 and order 4. Yes, they are order 6 and order 4. And second, you check whether these solutions are factorizable. Right, so if you check the previous structural solutions, they are basically solutions that is composed from smaller order solutions using the ring multiplication and the ring addition. Right, so and you actually see that in the gradient descent solutions, these solutions obtained by the empirical approach is also following the same factorization structures, showing that this analytical form also play an important role in determining the solutions in empirical sense. Right, so the factorization error is small, and finally, and what you see here is that this solution not only factorize, but they are factorized into the form that is constructed in the analytical formula. So that's actually very interesting, and this might give you the idea that maybe in the future, you don't need to use gradient descent, right? So there may exist another algebraic operation so that you can construct a solution that is similar to what gradient descent can achieve. Right, so in that case, like the solution that obtained by gradient descent is actually has symbolic representation. We don't know, but we might know later. Right, so maybe in the future there will be a new approaches to optimize neural networks so that the representation become very useful. Right, so this actually concludes the talk. Maybe in the future, instead of like praying the machines so that the machine can give you the right solution without too much issues, we might open the black box of neural networks and actually come to a different stage of training, and we actually know what's going on inside. So thanks everyone for the attention, and let me know if there are more questions.
Thanks, Dr. Tian. Yeah.
Yeah, thank you. Yeah.
Go ahead.
Thank you. Can you hear me? Yeah. Yeah. So I want on. So the phenomenon is observed that they are using such a specific structure to solve this modular addition tasks.
Yeah.
In a training setting where the only training data is this like additional task. I wonder, like in a real case, like in a complicated pre-training LLM, the math task is also trained with other like linguistics task. Like, is the same observation happen again, or they're doing?
Yeah. So I think that the two papers that I actually share, right? So they actually train. They basically like just directly check the pre-trained models people provided. So it's basically trained with all the data. So it's not only the synthetic data, the addition data.
I see. Thank you.
Yeah. So if you check these two papers, right? So the pre-trained language models use the Fourier features to compute addition. So this is basically they are basically checking the Llama models, right? So yeah. So these two are basically the papers that you can check. Yeah.
Thank you.
Yeah.
Okay.
Do we know why gradient descent favors this modular factorization structure?
Yeah, I think first of all, there's some hidden slides. Unfortunately, I didn't put this into this version. So you can actually show that the two global solutions, they are connected by a path of all zero losses. So for example, if you have solution Z, that is already a global solution for the objectives. You have another solution, which is Z times something, which is also global solutions by the property of the semi-ring structure. Then you can prove that these two solutions are actually connected by a path. And if you apply weight decay regularization, then the weight decay will favor simpler solutions.
I see. Okay. Yeah.
So that's an interesting phenomenon. Of course, it does not give you the full picture, because the full picture may be the case that you have two solutions that are not connected. Then that's the question.
Yeah.
But at least they give you some kind of idea, because the
this
solution is like a lower order. Yeah.
Right. And this holds also for Adam, or just like gradient with weight decay? Like if you add momentum, you will also have this same low complexity favoring?
Yeah, actually, all the experiments here are done by Adam. So this is Adam.
Oh, I meant theoretically though, yeah, but okay,
Oh,
yeah,
yeah.
thank you.
Yeah, theoretically, yes, because in the paper, I don't really analyze the dynamics. We basically analyze like what's happening after we go into the optimal solutions, right? So it basically applies to them as well.
Okay, got it. Thank you.
Well, okay. Cool.
So maybe one last quick question from the audience. Okay, if not, thanks, Dr. Tian again. And we're going to come back tomorrow, and then we will focus a bit more on this agent. And Dr. Tian going to chair the session. We'll see you guys tomorrow then.
Bye.
Thank you.
Yes,
Bye.
bye-bye.
Bye-bye.